Okay, this time we're going to look at partial fraction decomposition. And in partial fraction decomposition, we are looking at being able to reverse the process of adding fractions. So for example, right, if we add two rational expressions, 2 over x plus 1 plus 5 over x minus 2, well, we have to find a common denominator. So the common denominator would be the product of those two denominators, x plus 1 and x minus 2. And so the first fraction we need to multiply by an x minus 2 to the top and an x minus 2 to the bottom, so that we have that common denominator of x plus 1 and x minus 2. The second fraction, we're missing the x plus 1. So we have to multiply top and bottom by x plus 1 and an x plus 1. And then we have that x minus 2 as well. And so now that these two fractions have the common denominator, we can add their numerators. And in order to add their numerators, we use the distribution property. So we get 2x minus 4 plus 5x plus 1 plus 5, and that's all divided by the LCD. And now collecting like terms, we end up with 7x plus 1 on top, and over the LCD of x plus 1, and then x minus 2. And that would be the solution to the process. Now in partial fraction decomposition, we want to reverse that. And we want to start with 7x plus 1 over x plus 1 and x minus 2, and can we figure out this decomposition? That's the goal for doing this partial fraction decomposition. And when we have, let's think about fractions, numbers, right? When we have a number like this, 2 over 7, that's a proper fraction, versus something like 11 over 3, that's improper, right? And so when we have an improper fraction, we have, we can write it as a mixed number. 3 goes into 11 3 times with a remainder of 2. So 3 2/3 would be writing that as a mixed number, right? And a mixed number is a whole number plus a fraction, right? A proper fraction. And in doing this decomposition, says that in order for me to think about proper fractions here, that my first denominator had to be an x plus 1, because that factor appears in the denominator, and the second fraction has a denominator of x minus 2. So those are the two denominators. And so for this to be a proper fraction, since the numerator or the denominator was linear, we had to have a constant numerator. So the denominator was linear, we had a constant numerator for this to be proper fraction. So there's a constant up here that we're going to try to figure out, a, and likewise a b for that top of that numerator as well. And so now from there it's a matter of figuring out those constants a and b, and the way we're going to do that is by taking that equation and trying to solve, right, that equation for a and b. And in doing so, we're going to multiply both sides by the common denominator So we're multiplying both sides by the LCD to clear out the fractions. So then we have on the left-hand side x plus 1, 7x plus 1. And on the right-hand side, we have x, a times x minus 2, and a b times an x plus 1. And now from here, we're going to equate coefficients, right? When we add things together, we're adding like terms. So on the right-hand side, we have an ax minus a 2a and a bx plus a b. And then on the left-hand side, we still have this 7x plus a 1. And now this is going to form a system of equations. It tells me that, right, if here I have an ax and here I have a bx and there's a 7, well, that tells me that whatever a and b are, they're going to have to add together to give 7. So then I have an equation. 7 is equal to a plus b. Now the constants part, there's a constant 1 here, there's a constant negative 2a, and a constant of b. So that tells me that 1 is going to have to equal negative 2a plus b, because we add like terms. And so there's my second equation, that 1 is equal to negative 2a plus b. And so now there's a system of 2 by 2. We can solve that system. We multiply that top line by 2 and add it to the bottom line to get rid of the a's. So 2 row 1 plus a row 2. We get 7 times 2 is 14 plus 1 is 15. And then the a's drop out. And then 2b plus 1b makes 3b. So then we have 15 is equal to 3b. And that tells us that b had to be 5. And if b is equal to 5, back substitution would tell us a has to be 2. And so we have these two, we had those two coefficients. We had 2 over x plus 1 plus 5 over x minus 2 gave us that decomposition of that original fraction. It turns out that we can expedite the process. We don't necessarily need to solve a system of equations. We can use what's going to be called the cover-up method or the Heaviside method. So if x is equal to 2, then this factor goes away. And so I will be able to get b by substituting x equal 2 into that equation. So if I plug in x equal 2, we get, when x is equal to 2, it tells me that 7 times 2 is 14 plus 1 is 15. And then x equal 2 on the right-hand side, the 2 minus 2 goes to 0, and 0 times a is 0, but the 2 plus 1 is 3, and 3 times b is 3b. So then from there I tell directly that b was equal to 5. And if I do the same for the second factor, goes to 0 when x is equal to negative 1. So if I substitute negative 1 into that equation, then I get 7 times negative 1 is negative 7 plus 1 is negative 6. And on the other side, I get negative 1 minus 2 is negative 3a. And then the negative 1 plus 1 is 0 times b is 0. So I get a. From here, I get a, divide both sides by negative 3. I get a is equal to 2. So we can either solve a system, or we can use this cover-up method or the Heaviside method and figure it out. So again, when the denominator is linear and the numerator is a constant. And if the denominator is quadratic, that cannot factor, if the denominator is quadratic and irreducible quadratic, means that it doesn't factor, then the numerator has to be of degree 1 less. So the numerator would have to be linear for it to be a proper fraction. And those are the two types of denominators that you will work with, because remember the fundamental theorem says we can always factor a polynomial, right, into irreducible quadratics or linear factors, right? So let's take a look at an example here. If we have 5x squared minus 5x divided by 5, and let's say our denominator factors as x minus 2 a linear factor, and then x squared plus 1 is a quadratic factor. So for my linear factor, when my denominator is x minus 2, my numerator would have to be a constant, just a. And that x squared plus 1 does not factor further, so it's an irreducible quadratic. So for that denominator, the numerator has to be linear. So a linear would be bx plus c. And there is my decomposition now, would be to solve that equation for a, b, and c. And we can either equate coefficients, right, and form a system of 3 equations, right, because we have 3 variables, a, b, and c. We're going to have a system of x squareds compared with x squareds, and a linear term x with linear term x, and then the constants equate out, and you'll have a system, a matrix of 3 by 3. So the first step would be to multiply through by the LCD to clear out the fractions. And on the left-hand side, we'll get 5x squared minus 5x plus 15, plus 5, I mean. And then on the right-hand side, we have a. The x minus 2's will cancel out, so I have x squared plus 1 left over. And then for the second one, the x squared plus 1's cancel out, so I have x minus 2 times the bx plus the c. And so we can either form a system, right, looking at multiplying that out. We'd have an ax squared plus an a. We're going to have a bx squared plus a cx minus a 2bx and minus a 2c. So then we have the x squareds a and c and b would have to equal 5. And there's one of the equations. Using our Heaviside method, we can get a for free by plugging in x equal to 2. So if I put in x equal 2, this factor goes to 0, and so the only factor left would be that term involving the a piece. So substituting x equal 2 into that equation will give us 5 times 2 squared minus 5 times 2 plus 5 is equal to a times 2 squared plus 1 plus 0, right? Because the 0 times the bx plus c goes away. And now I'll solve that for a. We get 5 times 2 squared is 20, and minus 5 times 2 is 10. So 20 minus 10 plus 5 is 15. And on the other side, 2 squared is 4 plus 1 is 5, and 5a is on that other side. So we divide both sides by 5, and we got a had to be 3. All right. Now to get the other terms, to get the other coefficients, just have to plug in 2 different numbers, right? A number different from 2. So we can get c by setting x equal to 0. Right? We can get c because that bx term goes to 0, and then I know what a is. So if I plug in x equal to 0, then 5 times 0 squared minus 5 times 0 plus 5 is 5. And plugging in 0 for x, I get 0 squared plus 1 times a is a. And then 0 minus 2 is negative 2. And then 0 plus c is c, so I get 5 is equal to a minus 2c. And I know the value of a, right? A was equal to 3. So that tells me subtracting 3 from both sides, I get 2 is equal to negative 2c. So then c had to be negative 1. There's the value of c. And to get b, just choose any other number besides 0 and besides 2. We can get b by setting x equal, say, 1. It would work for any number besides 0 or 2, because we know those two numbers already, those two values for a. So if I plug in 1, 5 times 1 squared minus 5 times 1 plus 5 is 5. And then over here, on the other side, 1 squared plus 1 is 2. So I have 2a. And then 1 minus 2 is a negative 1. And then b times 1 is b. And plus that c. So now that's the equation where we know c is equal to negative 1 and a is equal to 3. So using that information, we'd have 5 is equal to 6 minus 1 times a b minus 1. And now using the distribution property and collecting like terms, we subtract 6 from both sides. We get negative 1 is equal to negative b plus 1. And then subtracting 1 from both sides, we get negative b is equal to negative 2. So b had to be 2. And so our decomposition was like this. 3 divided by x minus 2 plus 2x minus 1 over x squared plus 1 is going to equal 5x squared minus 5x plus 5 divided by x minus 2 and x squared plus 1. Now, those of you going on to take calculus, you'll see this again in Calc 2, the second semester calculus, where you're trying to find the intervals, right? You're doing integration, and this is one of the techniques of integration that you can use, because once you have this in this decomposed form, it's easier to deal with, right? So now if we have some repeated factors, if I have a denominator that has a repeated factor, we need to account for all possibilities, all possible combinations. So all possibilities. So for example, right, if I'm adding 1/2 with 1/4, well, I had my answer is 3/4. But if I decompose that 3/4, I had to account for a possibility of it having that repeated factor in the denominator. So if I have a repeated factor, I need to account for it. So for example, if I have negative 5x minus 19 divided by x plus 4 squared. Well, I could have a fraction that has that single denominator of x plus 4. So I have an a over an x plus 4. But I could also have a denominator that accounts for that repeated factor. of that x plus 4 squared piece. And my numerator would also be a constant as well, because it's a linear factor that was repeated. So I have a constant on top. And so this is what my decomposition would look like. And now clearing out our fractions, multiplying through by the LCD. On the left-hand side, we'd have negative 5x minus 19. And on the right-hand side, I have an A, and then an x plus 4. And then the second factor, I just have a B, and it went away. And here I can get B by substituting x equal to negative 4. So if I plug in negative 4 into x, I get 5, negative 5 times 4 is, negative 4 is 20. 20 minus 1 is 19. That tells me that B had to be 1 when we plug in negative 4. And now to get A, just choose any other number besides negative 4. So if I choose x equals 0, plugging in 0, I get negative 19 is going to equal 0 plus 1, 4 is 4, so 4A plus B, and I know what B was. So then solving that for A, I subtract 1 for both sides, I get negative 20 is equal to 4A, and dividing both sides by negative 4, I get B had to be negative 5. And so my decomposition would look like this. We have A was equal to, this is A, not B here. So I get negative 5 over x plus 4 plus 1 over x plus 4 squared. And that would be the decomposition for that fraction. And things get worse if we had a a repeated quadratic term. So maybe we have something like this. X squared plus 5x plus 5 divided by x squared plus 2 squared. Well, I would have to have a linear factor for my numerator. So my first numerator would have to be ax plus a b divided by that quadratic, x squared plus 2. And now to account for the repeated factor, my second denominator would have to be x squared plus 2 squared. But my numerator would have to be a linear factor, a cx plus a d. So this time you'd have a system of 4 by 4, right? 4 equations to, if you equated coefficients, you'd have a 4 by 4 system. And then using the Heaviside method, you'd have to use, right, you'd have to just plug in 3 sets of numbers, or 4 sets of numbers to figure them out. 4 different numbers. Right, I'd put in 0 for one of them, maybe 1 for another, and just keep it simple, right, using small numbers. But it will eventually work out. Anyway, I hope that helps.